This video will show you how to make a moving phase boundary simulation using the graphical mode version of the Diffusion Module, also known as DICTRA. This example only uses 2 elements, so it can be run even if you do not have a license for the Diffusion Module using the free demo database packages included with your software. It can also be run with the free educational package. In this video, I will show you 3 ways to make a moving phase boundary simulation. All 3 examples use the same alloy, a steel with 0.15% carbon. All 3 examples simulate the growth of ferrite, BCC, into austenite, FCC. The first 2 examples are isothermal, and the third is non-isothermal. The calculation is based on Diffusion Module Example 2, which can be accessed from the example files icon on the home screen of Thermo-Calc, Diffusion Module DICTRA. If you want to run the example as it is, double-click on the example file, then right-click on the top node and select Perform Now. In this video, I'll walk you step by step through how to set up the calculation and discuss the results. You can learn more about moving phase boundary simulations in our online help system. From the main menu, go to Add-on Modules and Property Model Libraries, Diffusion Module DICTRA, Quick Start Guide Graphical Mode, Moving Phase Boundary Simulations. Here you can learn about the theory behind the simulation and more. For the first example, both phases are assumed to be initially homogeneous, and the transformation temperature is 1050 Kelvin. The initial thickness of the austenite is 2 millimeters, and an initially very thin ferrite, 1 nanometer, is also present at the start of the simulation. To begin the calculation, click on the Diffusion Simulation template from the home screen of Thermo-Calc. All the nodes we need to run a diffusion simulation will appear in the project pane. Select the System Definer node. Then select the Demo, Steels, and Fe Alloys database package. This will load both the thermodynamic and mobility databases. Select the elements iron and carbon. When you're making a diffusion simulation, you do not set the material composition because compositions in the diffusion module vary with distance. Next, select the Diffusion Calculator 1 node, which opens the diffusion module. We will accept the default composition unit of mass %, but we will change the length unit to micrometer. We will accept the default planar geometry. Next, we will define the region. All diffusion simulations require at least one region to be defined. Our simulation has 2 regions, ferrite and austenite, so we need to add a second region. Click the plus sign next to region. A second tab appears, so we have a tab for each region. Click on the left tab and type in ferrite in the name field. This changes the name of the region to ferrite to help us identify which region is which. You can change the order of regions at any time by right-clicking on the tab and selecting Move Right or Move Left. Click the Ferrite tab. In the Width field, enter 0.001 micrometers. Notice that when we entered a width, a visual representation of our region appeared in the form of a colored line, known as the domain. There's also an outline of a rectangle representing the other region, which is yet to be defined. We'll allow the program to automatically distribute the grid points, which was a feature added in Thermo-Calc 2025B. If you have an earlier version of the software, select Linear with 10 points. Next, we need to select our phase. There are several phases listed, so if you do not know which phase to select or their compositions, you can quickly calculate a phase diagram to determine this information. Right-click on the System Definer node, highlight Create New Successor, and select Equilibrium Calculator. Under Calculation Type, select Phase Diagram. Right-click on the Equilibrium Calculator, highlight Create New Successor, and select Plot Renderer. Then right-click on the plot renderer and select Perform Now. Once the calculation is complete, an iron-carbon phase diagram will appear in the results pane. We're interested in the phases present at 1050 Kelvin for a steel with a carbon content of 0.15 mass percent. So zoom into that region to get a better look. At 1050 Kelvin with a carbon mass percent of 0.15, we can see that the only phases present are FCC and BCC. You can see the equilibrium information by hovering your mouse around 0.15 mass percent carbon and 1050 Kelvin, then right-clicking and selecting Add Label, then Show Details. The carbon content of the BCC phase is about 1e to the -4 in mass fraction carbon, which is equal to 0.01 mass percent carbon. Remember this number because we'll use it when we set up the diffusion simulation. Close the dialog box and return to the diffusion calculator. Set the phase to BCC-A2, which is one of the two phases we saw in the phase diagram. Now that you've selected a phase, if you hover your mouse over the region, you'll see information about that region. Next, we'll set the composition profiles. If you have an older version of the software, click Edit next to Composition Profiles to access the settings. We'll leave iron as the dependent component and linear variation as the initial carbon profile. You can read about these options if you hover your mouse over the drop-down menu. Enter 0.01 in both fields. This represents carbon going from 0.01 mass percent on the lower left-hand side of the system to 0.01 mass percent on the upper right-hand side of the system. This is the mass percent we saw in the equilibrium calculation, and we can see a visual representation of this once we enter a thermal profile. So let's do that now. Scroll to the bottom of the window to the Thermal Profile section. We're doing an isothermal simulation, so leave that selected. Set the temperature to 1050 Kelvin and the simulation time to 30 hours. We can now see the visual representation of carbon going from 0.01 mass percent on the lower left-hand side of the system to 0.01 mass percent on the upper right-hand side of the system. Now let's set up Region 2. Click on the Region 2 tab and name it Austenite. In the width field, enter 2000 micrometers. Notice that the domain turned almost entirely yellow. This is because the austenite region is so much larger than the ferrite region that the ferrite region is too small to see. Therefore, it's represented by a dashed outline. If we were to enter 0.001 in the austenite region, the two regions would be the same size, so you could see both regions as solid colors. But in our simulation, austenite is 2000 micrometers, so I'll change it back. Once again, we will allow the program to automatically distribute the grid points. But if you have an older version of the software, change the type to geometric with 50 points and change the ratio to 1.05. Set the phase to FCC-A1, which was the other phase we saw on the phase diagram. Regions are always separated by phase interfaces, and the phases must always be different for each region. Now we will set the composition profiles. Again, if you have an older version of the software, click Edit next to Composition Profiles to access these settings. Enter 0.15 in both fields. Notice that when we do this, we can see a visual representation of this in the Visualizations window. This is the material composition, and entering it here means that carbon will go from 0.15 mass percent on the lower left-hand side of the system to 0.15 mass percent on the upper right-hand side of the system. Now click on the Plot Renderer 1 node. Change the x-axis variable to time, hours, and change the y-axis variable to position of interface. Change the units to micrometer, but leave the default interface of ferrite, austenite. Now click Perform at the bottom center of the program. Once the simulation is finished running, a plot will appear in the Visualizations window. The plot shows the Ferrite-Austenite phase interface position as a function of time. The plot has the parabolic appearance that is characteristic for many types of diffusion problems. We can see that the curve does not flatten out, which tells us that ferrite has not reached equilibrium at this time. We can go back to the diffusion calculator and increase the time to 300 hours, then click Continue. Once the calculation is done running, return to the plot renderer node, and we can see that BCC reaches equilibrium when the curve flattens out. Notice that there are now two colors on the plot line. The blue section represents the first simulation of 30 hours, and the red section represents the continuation to 300 hours. Next, we will add a second plot to look at different variables. Right-click on the Diffusion Calculator node, highlight Create New Successor, and select Plot Renderer. Right-click on the new plot renderer and select Rename so that we do not confuse the two plots. Name the node Composition Profile C for carbon, then press OK. Set the x-axis to distance, micrometer, all regions. Click Show More. Then uncheck the box next to Automatic Scaling for the x-axis and set the lower limit to 0, the upper limit to 2000, and the steps to 200. Set the y-axis to composition, carbon, mass %. Make sure the time unit is set to hours, then place your cursor before the 300 in the time field. Add 0, space, 1e to the -4, space. This will plot the simulation for all three of these times. Right-click on the Composition Profile Carbon Plot Renderer node and select Perform Now. A second plot will appear in the results pane, which shows the mass % of carbon over a distance from 0 to 2000 micrometers at the 3 times we set: 0, 0.36 seconds, and 1,080 seconds, or 300 hours. Now I will show you a second way to set up this simulation. Right-click on the Diffusion Calculator 1 and select Clone. We now have a second diffusion calculator that has the same configuration as the first. Select the Ferrite tab and delete the region by clicking the minus sign next to Region. This leaves us with only one region, Austenite. Select Show Left Interface Boundary and select the BCC-A2 phase. Leave the driving force as it is. This means that the simulation will start with Austenite only, which is the FCC phase, then ferrite, which is the phase BCC, will form when the driving force for this phase exceeds 1e to the -5. Right-click on the Diffusion Calculator 2 node, highlight Create New Successor, and select Plot Renderer. Set the x-axis to time, hours. Select the y-axis drop-down menu and notice that there are not that many options. For instance, Position of Interface is missing. This is because the region is not yet created. In the first method, we entered both regions, but in this method, we only enter one region and ask the simulation to create the second region once it becomes stable. In order to get additional plot options, we must perform the simulation. So right-click on the Plot Renderer 3 node and select Perform Now. Once the simulation is finished running, we can select Position of Interface from the y-axis drop-down menu. Change the units to micrometer. Our interface has also appeared. When a region with a phase is created during simulation, such as BCC in this example, an R is put in front of the phase name in order to give the new region a name. Click Perform again. We now have a similar plot to the one we made in the first example. Finally, I'll show you how to run a non-isothermal simulation in the same setup. This means that the temperature will change. If we look at the phase diagram we created, we can see that at 0.15 mass percent carbon, only one phase is present above about 1130 Kelvin, FCC. As cooling occurs, the BCC phase will appear once the temperature falls below approximately 1130 Kelvin. Note that if we have a thin ferrite layer present at the start of the simulation, then it would dissipate if we were above this temperature. Therefore, we want to run a non-isothermal simulation that starts with a single region, austenite, and adds ferrite once it's stable. Right-click on the Diffusion Calculator 2 node and select Clone. This gives us an identical diffusion calculator. Select the Diffusion Calculator 3 node and select Show Left Interface Boundary just to remind ourselves that BCC will be introduced once it's stable. Under Thermal Profile, select Non-Isothermal. A table appears where we can enter our times and temperatures. Set the initial time to 0 and the temperature to 1200. Hit Enter and set the second time to 0.3 hours and the temperature to 1050 Kelvin. The final temperature, 1050 Kelvin, is maintained during the entire simulation, which is 300 hours in this example, but it's only shown for 0.3 hours. Notice that a visual of the thermal profile has appeared in the visualization window. To get a visual of the entire thermal profile, hit Enter and set a time of 300 hours and a temperature of 1050 Kelvin. The initial temperature of 1200 Kelvin is now quite small in the visual, so you can zoom in to get a better view. We must now run the calculation before we add a plot render node. This is because the austenite phase, BCC-A2, will be created during the simulation, so it cannot be plotted until after it's created. Right-click on the Diffusion Calculator 3 node and select Perform Now. Once the simulation is complete, right-click on the Diffusion Calculator 3 node and select Create New Successor, Plot Renderer. Set the x-axis to time, hours. Set the y-axis to position of interface, micrometer. And notice that the austenite phase, which was created during the simulation, is present. Now select Perform at the bottom center of the program. Once the calculation is complete, a plot will appear in the results pane, which is similar to the two isothermal versions we created. If you liked this example, don't forget to press the like button, and feel free to leave a comment about the type of video you'd like to see next. We are constantly working to create new examples, so make sure to subscribe to our channel so you don't miss out on any new videos. You can watch all of our videos at Thermo-Calc.com in the Video Tutorials section.